Well, hi everyone, thanks for coming. Sorry for the technical delay. My name is Jim Leonard, and if you remember me from the demo scene, I was called Trickster, and I was in the demo group Hornet. If you might also know me, if you're not familiar with the demo scene, as the co-founder of MobyGames.com. But I'm not here to talk about either of those things. I'm here to talk about a waste of time I did in 2004. And it's called 8088 Corruption, and it claims to display full motion video on a really old, slow machine. So I was going to ask how many people have seen it by show of hands, but I think I'll just go ahead and show it to you. I apologize for the colors. They're probably going to be a little bit off because of the camera and everything.
Hi, this is Jim Leonard. The reason I'm interrupting my own presentation with this voiceover is because at this point in the presentation, the hall that I was talking in lost power, and for the next 12 minutes, I had no projector and I had no microphone. So that portion of the video is silent, and what I'm going to do is go ahead and fill it in with the missing pieces. When I'm finished and my audio is turned back on, I will cut back to the video. So, 8088 Corruption is a program that plays video that is full motion, that's 30 frames per second, full screen, in color, and has synchronized audio, all on a 1981 IBM PC with CGA, and of course a Sound Blaster for audio. So what? Why should you care? Well, an 81 PC with CGA has a very slow 16-bit processor. If you're lucky, 256K of RAM. 16 fixed but ugly colors, and more importantly, in all 27 years it's been around, it's never displayed motion video before. So how did this start? Well, like most demo scene projects, it started as a dare. I was at work with a couple of friends joking around in a nerd-like way, like nerds are prone to do, and we were saying things like, I can create fractals on my abacus, or I can communicate with a modem by whistling into the phone, and stuff like that. And I shot out, I can display video on my XT. And later that day, I got to thinking about it, and I did some informal calculations and thought that, yeah, maybe I could get something resembling video on my XT with CGA. So I mentioned it to a friend, and he essentially dared me to do it, so that's how I started. I got something working and submitted it to the Wild Compo at Pilgrimage 2004. That was a small demo party in Salt Lake City, Utah, and was very pleased to win the Wild Compo. And because of that, the Scene Awards picked it up, and they asked me to create a video to prove that it was in fact me, that it was a real IBM, and that I wasn't cheating or anything like that. So I created the video, and I put it on Google Video and YouTube, and they nominated it under the category Most Original Concept. And I didn't win, but it was very flattered to be nominated. And I didn't think much of it after that until January of 2006, when someone posted a link to the video on the social news site dig.com. It quickly shot up to the top of the front page with 2,700 digs and was featured on that week's Dignation television show. So that's why I was asked to speak in front of you today. So how do you do this? How do you solve a problem that is fundamentally impossible? It isn't impossible, but you have to come up with a detailed list of specifications. First, you define the problem. Write a program that displays full motion video on low resource hardware. And then you research that hardware, the output device, what's possible. And you research the input device. The input device, of course, is going to be the human brain. People are going to be watching this, so what looks best to the human brain? And once you have a list of your input and your output specs, you have your entire list of specifications, and you have a goal that you can work toward. So let's actually start with the input device. The human brain is a pattern recognition engine. In fact, it's the best in the world, at least until Skynet comes online. And as such, it works better with frequency than amplitude. And what I mean by that is the human brain works best the more samples you feed it. The samples don't have to be very good, but the more you feed them, the more it has enough information to lock onto a pattern. For example, you can take a sound clip of someone talking, and you can turn it into a 16 kilohertz 1-bit sample and a 1 kilohertz 16-bit sample. And both will take up the exact same amount of space, the same bandwidth, except that the 16 kilohertz sample, while incredibly scratchy because it's only 1 bit, you'll be able to understand. However, the 1 kilohertz 16-bit sample, you're not going to understand. It's going to sound like bludgeoning a walrus underwater or something. It's muddled and you can't understand it at all. So that's just one example to try to illustrate that the brain works better with frequency than amplitude. And the same concept extends to the human visual system. Now in this slide I'm showing you two different examples of video. One is 60 frames per second in 1-bit color, that's black and white, and the other is 2.5 frames a second in full 24-bit color. Both videos use the same bandwidth, that is, they take up the same amount of disk space, the same amount of space in RAM, but only one can be considered motion quality video, and that is obviously the example on the right. So once again, this is a further example of how the brain deals better with frequency than amplitude.
So in trying to solve this problem, I started out with what looked best. I did some empirical testing and took full motion video, 60 images per second, not stuff you grab off of YouTube, because that maxes out at 30. I actually filmed stuff myself and converted it to 60, created integral divisions of that, 30, 20, 15, 12, etc. frames per second. Came up with 30 frames per second is the minimum acceptable quality to call it motion video. And then did the same thing for audio, and I came up with the result that 22 kilohertz is just about acceptable for something like music, and that's what you just heard. So then we moved to the output device. To determine what was possible, let me give you a small history of CGA here. CGA is a memory adapter that has a little bit of RAM on the card, and it is constantly scanning that RAM, and whatever is in that RAM is what's displayed on the screen. So essentially, however fast we can update that RAM is how fast we can change the contents of the screen. So some more empirical testing, I wrote a small assembly language routine that measured how fast the CPU can actually move data into the CGA adapter RAM, and came up with 160K of data per second moving to the CGA card. So now we take all of our results and we figure out what's possible. We found out that moving data to CGA tops out at 160K, 30 frames per second is our minimum acceptable quality. Audio takes up 22, so we subtract the audio from how much memory we can move into CGA, and we get 4.6. So our final result is 4.6K is the maximum amount of RAM we can copy each frame to stay within our 30 frames per second target. So when we research the output device, what are our options? Well, graphics modes use 16K, that's greater than 4, so that's not an option. 80 by 25 text mode uses 4K. However, 80 by 25 text mode has a problem with snow. And if this sucker boots up, I can give you an example. When you write direct, the memory in CGA is not dual ported. So when you try to write directly to screen RAM, I don't know if you can see it. See how there's snow? There's all this flashing snow on the screen whenever the screen's updating. You can't use that. The video would be unwatchable. So we have only one mode left, and that's 40 by 25 text mode. So that's our final result. we have to, whatever we're going to do, if we're going to solve this, it's got to be in 40 by 25 text mode. So how the hell do you convert images to display in 40 by 25 text mode? The converter went through 3 different iterations. One was a resolution-centric approach, which was very naive, and you'll see why in a second. The second was I tried to attempt some dithering or halftoning, and that had pluses and minuses. And finally, there was a brute force linear time comparison, which worked the best. So let's give you some examples of this. The first idea was to emulate character graphics. I don't know if any of you are familiar with like the old CX Spectrum or anything like that. The Spectrum displays graphics that are actually made up of 8 by 8 tiles. It's actually the character generator. It's text mode, but it's like a custom font. I'll have an example in a second. So I was thinking 40 by 25 text mode uses the same thing. It's 8 by 8 character cells. So only 2 colors are allowed per cell. And if you count out all of the individual dots that are actually displayed on screen, it comes out to 320 by 200. So this was my reasoning, that I would start with a 320-200 picture and try to map it exactly as best I could to all the dots on the screen. Here's what ZX Spectrum stuff looks like. If you look at the zoom in on the leg, you can see it's kind of blocky, and if you go ahead and break it out, my idea was to emulate that. And the difference between the Spectrum and the IBM is that on the Spectrum, you can change all of those pixels in each block. On the IBM, you can't. So this was the basic conversion. Remap colors using the 16-color palette, determine the 2 most popular colors, remap it again using just those 2 colors, and compare to all possible character and color combinations and use the best one that matched. And I figured it's got graphics characters, it's got lines, it's got shaded characters, it should work, right? Well, the initial results weren't that great. I'll give you a second to look at those. These were the test pictures I used in determining everything. I was happy to see that some stuff was a perfect match, which makes it look almost as if you drew it in that mode. Well, not really. But obviously the biggest cons were that since entire areas were mapped to a single flat color, the colors were not only wrong, but they completely obliterated all picture detail. So as a knee-jerk reaction, I went completely the other way. I figured, okay, well, forget about trying to match resolution exactly. Let's just look at color. Halftoning, or dithering, depending on how you use it, is the process of trading spatial resolution for color resolution. And the IBM character set includes a 50% on-off checkerboard character. And I figured if I use that, I can try to simulate a crude form of halftoning and come up with different colors. So there's the shaded characters up there. The 177 is the one that I used. And by using all of the colors and eliminating duplicates, you can get a fairly reasonable facsimile of more colors. So that one was really easy to do. I just compared the process was resampling the 320-200 picture down to 40 by 25. So I had exactly 1 pixel to one character pixel lookup to do. And you resize it, and then you use the closest match. Well, the colors are better, but it looks like ass. I really almost submitted this to Pilgrimage. I'm glad I didn't, because the colors were better. Because the text character is also 177, I had less memory to fling around, so I could have probably done even faster updates of the screen. And the conversion process is really fast, but the con was big enough that obviously I did not. So at that point I was stuck, and this is where my collaboration with God Jr. really came in handy. I had mentioned something like, if only we could get results, we're halfway between these two. And he suggested an idea that led to the idea that was used in the final converter, which is resampling both the picture and the character set to be compared bilinearly down by 50% so that they smooth out. And I'll explain this in a second. So, well, as I just said, you still take the same 320 by 200 picture, resample it 160 by 100 smoothly. You don't drop pixels. You use a bilinear resize so that it gets all kind of smooth in the process. It aliases in the process. Anti-aliases, rather. And then divide that up into 4 by 4 cells and compare each of those areas of the original source bitmap with a similarly resized character color combination in the character set. You resampled that as you compared as well and used the closest match. And that obviously had the best results. Now, the projector the gamma is a little off, so I apologize for the dark areas in the clown, but at least now you can see that the colors are better. You can see that the dark outline around the cloud's eyes. and so forth. So the pro of this, obviously, is that detail and color is preserved probably as best it can be. This is a linear search, which leads to its disadvantage. The conversion process is so slow it can be measured in seconds per frame, which sounds crazy considering that, this is the conversion wasn't done on this machine. Trust me, this is like on a Pentium 2 gigahertz. It takes seconds per frame because you have to do all those comparisons to get your final 1,000 characters. It's over 1 billion comparisons per frame. So why did this third process work best? Mainly because the checkerboard character, when you also resize it down by linearly 50%, the pixels blend together. And those blended pixels become solid colors, and they match better with solid areas in the source bitmap. And because the characters are resized at the same ratio as the bitmap that they're being compared to, you can still get these perfect matches, which preserves detail. So that's the converter, but the converter is only half the story. It is only 40 by 25 text mode, so in order to, how do you win a wild compo with something written in text mode? You have to choose your source material very carefully. I mean, the stuff that you saw in the demo was not by accident. It was very deliberately chosen. As I mentioned before, the human brain works best with familiar patterns. It needs a lot of information to make matches, but familiar patterns obviously would be better. So faces are good. Your brain has been learning how to recognize faces ever since you were born. Human movement, like walking or dancing, is also good. Try to avoid complicated backgrounds, tiny details, stuff that isn't important to the focus of the material that you're trying to present, that is just going to give the converter a hissy fit and trying to figure out what to choose. And finally, a little social engineering never hurts. I knew that my audience at Pilgrimage would be full of demo sceners, and I figured Tron would be a pretty good thing to show that people would recognize. So what I'd like to do is give you yet another example, if I can get this functional, of how important it is to choose source material. Okay. So again, this is an example of how important choosing the source material is. This didn't convert well. It's complex characters. It's a lot of dark stuff, which unfortunately this monitor is not very good at reproducing. But because it has faces, human movement, and is an easily recognizable pop culture reference, I'm sure you guys are going to be able to figure out what it is.
I repeat, we are under attack!
Only human.
Dodge this.
Over an hour. All right. So again, that was probably a pretty bad conversion, but at least you could tell what it was. I was going to talk a lot about the player, but I'm really short on time, and to be honest, there's not that much to the player. This is the surprising part. When people saw this, they thought that all of the heavy lifting was in the player, that it was some, physics-defying assembler that I had written or something. And as you just saw, most of the heavy lifting is done by the converter. The player is very simple. It fills up as much RAM as it can with audio and video data, and then starts the playback and divides into two code segments. One is a main code, which tries to just constantly keep loading off of disk and keep the queue full. And the other is an interrupt handler that at the desired frame rate frequency sends code pulled from, sends data pulled from the queue and sends it to the CJ frame buffer in the audio. And that's pretty much it. If the queue can't stay filled, like you've got too high a frame rate or your hard disk is too slow, the main code will pause playback until it's full again. Now, so far you haven't seen any rebuffering. There's a final example I'll have later that does rebuffer. You'll see that in action. The whole player was engineered with the idea of how to maintain audio-video sync. Nothing pisses me off more than watching a video and slowly having the lip sync drift off, either forward or backward. So I knew, I mean, again, to complete the illusion, the audio had to stay in sync, or it would have looked really shoddy. So I store the data in chunks, and each chunk has a frame to put on screen and the audio to display for that frame. To get the right timing, I set the sound card's audio buffer to the length of that frame. The nice thing about sound cards, for even as old a machine as this, is that when sound is done playing, it fires off a hardware interrupt. So the hardware interrupt handler that I wrote updates the next audio buffer and at the same time slams the next frame up on screen. So the sound card is driving the entire system. The CPU is not even involved there. And as a result, since every frame is locked to the next piece of audio that's going to get played, it cannot get out of sync. Some people have compared 8088 corruption to a lot of things, some of which you can see up there, ANSI Animation and things like that. I never understood the ANSI comparison. It's not ANSI Animation at all. It doesn't use ANSI sys in any way, even though it certainly looks like it does. You know, ANSI art is painstakingly crafted by artists, and if you're not familiar with ANSI art, I suggest you go check out Radman's talk, which I don't know what it is, but go see his talk. He's going to talk about ANSI and ANSI artists and things like that. And artists almost always produce better results, so I never understood the comparison. If there are any video compression geeks in the audience, you could compare what I just showed you to a vector quantization codec that uses a fixed codebook, the codebook, of course, being the CGA ROM font and all of its character combinations. But it's not really a codec because there's no actual decompression on playback. It's loading completely converted frames off of disk. Not only that, but I didn't start with a traditional codec like Cinepac or DivX and try to port it backwards to work on something slow. I started with the hardware's requirements first and went forward and saw what I could do with that. So I consider it more transcoding than actual compression. And another comparison is, you know, people have accused me of using AAlib or libcaca or the monotext module of libggi. These are C libraries that started in Unix and eventually got ported to DOS and Windows that convert graphics into text. But they use a completely different method. They're meant to be real-time conversions, something you plug in. There's like versions of VLC and Zinni and other Unix players that can play video through these things. Why you would want to do that, I don't know. And they don't produce as good a job because they're terminal agnostic, meaning they don't have access to the actual text data, the font data that they're using. So they have to come up with a generic table of what might look good in grayscale, which is the AAlib example on the left, or the same thing in color, which is that's a libcaca example, actually. So how can this thing be improved? Everything about it can be improved, actually. Nothing's correct on the first try. The player itself updates this, since the sound card is slamming video to CGA RAM whenever it wants to. There's shearing. So on the scroller probably didn't look very smooth, and it might have torn a little bit. That's because it updates whenever it wants. Since the sound card interrupt is driving the whole system, the system timer tick interrupt is actually free. You could use that to simulate a vertical retrace interrupt. And instead of writing directly to visible screen RAM, you could write to off-screen RAM and then do a nice clean page flip. You could also probably use EMS to buffer, but I consider that cheating because I don't know anyone other than myself who still has an EMS board in a machine like this, so I didn't implement it. Video preprocessing could have helped as well. One thing that shatters the illusion a little bit is that this doesn't change very much at all, but it does change slightly. The problem is that it leads to these massive changes in the converted output. So preprocessing the source for video noise, temporal video noise, would help eliminate that sparkle. You could also, if you've got decent temporal noise filtering and or your source doesn't move very much, you could start to do actual compression. You could compare the later frames to the previous frames and only store the changes between them. And then if you can write an assembly routine that can update the frame with just those changes at the same rate or faster than a full move, you can achieve actual compression. Now, if you combine preprocessing for temporal noise and compression, you can try to achieve the holy grail of 60 hertz screen updates. This is double the frame rate you get off of videos off of Google Video, YouTube. If you can update the screen at 60 hertz, there's a lot of extra stuff that you can do. It's technically possible right now, but there are some caveats. You're updating 4K per frame instead of, well, you're updating this is actually a mistake. You're updating 2K a frame, but at twice the rate. And at that rate, the CPU is spending more time updating the buffers than it is actually loading from disk. So it is actually currently impossible to avoid rebuffering. You'd have to implement less data rates, like I mentioned before, with compression or something. Or you'd have to cache the entire thing to EMS, which, again, I consider cheating. However, just to give you an example of how eerily realistic it looks like, I have an example. Let me do this real quick. This will rebuffer. So it'll pause 3 times when it plays. Again, I apologize. Oh, uh-oh. Can I lose this again? Hold on a sec. If it's not recording, it shuts off. Okay. Again, if you can see the monitor, the colors are more accurate. So if you can see it, I stress you to take a look at that. So what you get with 60 hertz is eerily realistic motion. So anyway, that's that example. "60 hertz motion, as you just saw, is very close to the limit of the brain's ability to actually discern individual events in time. So it's eerily realistic, again, if you can avoid the rebuffering issues, because that pretty much kills the illusion. Another thing you can do if you can update the screen 60 times a second is that you can actually get a better conversion. Hopefully the image on the right looks better than that on the left. If you keep track of errors during the conversion, you can push them forward. You can dither them forward in time, much like Floyd Steinberg dithering tries to distribute errors left and right on the line as it scans down. And so you can create a second frame to be mixed with the first one that fills in the gaps in the error in the original conversion. And since the screen is updating 60 times a second, it's fast enough that they kind of blend together. And so you get a result similar to the image on the right. Hopefully it looks a little bit better. If you look at the color gradations of maybe above his eye, the eye is rounder, for example. So you can pull that. If you wanted more resolution, you can also tweak CGA into a 50-line mode, where the first top 4 scan lines of each character is displayed instead of all 8. This doesn't give you any additional resolution. You don't get more resolution from this, but you do get more flexibility in choosing matches. So you can try to get a more higher res thing there. No, it displays the first 4 rows and then immediately switches to the next row. So what did I learn, and hopefully what can you take away from this, if anything? Know your output device. Having a goal makes it interesting and engaging. I specifically said 30 frames per second on this piece of crap. And so if you stick to that, it can be, that was the goal. That was the challenge, to keep going. And again, if you're trying to do something like video on a low resource, this is the same thing with demos too. If you want to write a demo for a low resource platform, focus on the specs of the machine and work backward from them. Don't try to start with an existing code you have for a 386 and port it. It's not going to be applicable. And know your audience. Know your input device as well. Know your audience and experiment. And challenge yourself, because stupid ideas are, for some reason, usually the most interesting to work on. I was going to talk more, but I'm afraid I'm out of time. No? Actually, I've got a little bit more. Okay. All right. Now I'm going to gripe. About 9 months after ADA, this is extra, after 9 months after ADA corruption was posted to Google and YouTube and viewed nearly 50,000 times, VH1 started showing these classic bumpers meaning like a piece of video you display between program segments or something. And it showed a PC of old vintage showing video in text mode with a cheesy MIDI soundtrack. It may have mostly been coincidental, but of course it caught my eye. Now this isn't going to play, but I do have it. If you want to see an example of what I'm talking about, give me a sec here. Very good. And that's part of my gripe, which I will get to in a second. I hope this works. Now, the first time I saw that, I thought that was cool. And then after I did, after I thought about it, it actually started to piss me off. Because, okay, hold on, let me see if I get to the next slide here. Okay, well, obviously it's ripping off AAlib. No thought went into it at all. They just ran stuff through AAlib and converted it. The frame rate was unnecessarily low. I just showed you 60 frames per second on a slow machine, and then they've got a better one, and it's only doing 12. And the music was unnecessarily cheesy. General MIDI was bad, but it wasn't that bad. And here's the non-obvious gripes where I show you what an incredible nerd I am. Other things that pissed me off about this is that the distortion was inverted. Notice that the lines are actually thinner in the middle than they are at the end. That means the screen is bending inward, not outward. I never got that. After the whips, there's no sync. It's not a real text mode, for example. Yes, I actually counted the letters. And most importantly, the computer used in the shot, as you notice, was a PS1. That's a 386 with VGA. It's capable of actual video. They could have, should put up a Spectrum or something like that. Yes? They could have at least turned on the monitor. Very good. So that's about all I have. My email is here. You can download all of it. And after the con, I will have full source code up for everything. And as a perfectly shameless plug, please buy Mind Candy Volumes 1 and 2, which you can get from myself or Andy Voss, who's also in the audience. And that's it. If you have any questions, please feel free to say me. So, and before we go, are there any questions? Yes?
Did you look at any other demos out there before you really got started that did essentially
Something like this?
the one thing I want to say, the first thing I thought was especially the girl dancing would be on the Amiga Spaceball kind of thing.
Well, that was certainly an inspiration. Probably a better thing was, did I look at like any text mode demos or something like that? Well, yes, the girl dancing was definitely an inspiration. State of the Art was one of the first Amiga demos I ever saw, and of course it blew me away. And I someday hope to reproduce that kind of video compression on this thing as well, but one step at a time. No, I didn't explicitly look to try to duplicate it. If I did, actually there was a demo in the late 90s for DOS that did in fact take video output from an emulator of state of the art and run it through AAlib, and that was it. And that was the demo. And it didn't look too good, as you can imagine. Actually, yes?
I have seen some productions of
CGA cannot, okay. Could I have modified the font table to get better matches? CGA does not allow you to do that. Now, if I had EGA or VGA, yes. But if I had EGA or VGA, I probably would have done a completely different track. I would have probably tried to do like the state-of-the-art vector stuff or something along those lines. Actually, sorry. Yeah. No, I am pointing at you, sorry.
Okay. How big are these videos once you're actually compressing now?
Very small. They are minuscule. The Matrix one you saw was over a minute long, and it was, I'm going to have to wait. Okay, it takes about 15 seconds to do a directory listing on this. I apologize. I think it was about 5 meg total. So you could load this onto a 10 meg MFM hard disk. It should still play if you have that old a machine. Yes, sorry about that. Yeah, it's 5.4 meg. So they're very small. I mean, each video frame is 2K, so multiply that up by 30 times a second, that's 60K, and then the audio is 22, so it's 82K a second. So they're pretty small. Yes?
Question, how did you get the 5 meg file into that machine?
I have a Ethernet card that magically works in 8-bit mode, so I did that. But before that, I had a parallel cable, and I would do it with fast links. Yes, Andy? Where did I get the music from? For the original one? I shamelessly stole it. It's Goa Trance from the group Space Cat. It's a 2003 tune, and every time I heard it, that middle section, I kept thinking, wouldn't it be great to have that in a demo? So, anything else? Anyone else? No? All right, well, thanks for coming.